In all of time, on all the planets of all the galaxies in space, what civilizations have risen, looked into the night, seen what we see, asked the questions that we ask.
We know that the galaxy is awash in water. It's awash in organic molecules and complex chemistry.
have any hope of finding alien life, we have to know what to look for. But where do we begin? How do we narrow down a seemingly infinite set of possibilities? There's one thing we know for sure. Nature will have to play by her own rules. No matter how strange alien life might be, it's going to be limited by the same physical and chemical laws that we are. On top of this, each alien environment will further limit what kinds of life forms can evolve there. Despite these natural boundaries, the possibilities are staggering to imagine. Trillions of planets, each a unique cauldron of chemicals undergoing their own complex evolution. To guide our thinking, this museum of alien life will be divided into two exhibits. Life as we know it, home to beings with biochemistries like ours, and life as we don't know it, home to beings that challenge our concept of life itself. Before we venture too far into the unknown, we have to ask ourselves, what if alien life is more like us than we think? If there's one feature that unites us with the other specimens in this museum, it's carbon.
Carbon is ubiquitous. It's one of the most common elements in the universe, and it's very good at forming large, stable molecules.
Carbon has the rare ability to form four-way bonds with other elements and to bind to itself in long, stable chains, enabling the formation of huge, complex molecules. This versatility makes carbon the centerpiece in the molecular machinery of life. And the same carbon compounds that we use have been found far from Earth, clinging to meteorites, and floating in far-off clouds of cosmic dust. The building blocks of life, drifting like snow through the universe. And if alien life has selected other carbon compounds for their biochemistry, they will have plenty to choose from. Scientists recently identified over 1 million possible alternatives to DNA, all carbon-based. If we ever discover other carbon-based life forms, we would be fundamentally related. They would be our cosmic brethren. But would they look anything like us? If they hail from Earth-like planets, we could share even more in common than just our biochemistry.
What would life be like on other planets if it has evolved? Would it be like the world today here on Earth? Or would it be completely different? There are those who argue that from the argument of convergent evolution, if conditions on other planets are similar to here, then we would see very similar life forms. Animal and plant-like organisms that look very familiar.
Earth, certain features like eyesight, echolocation, and flight have evolved multiple times independently in different species. This process of convergent evolution could extend to alien planets like Earth, where creatures face similar environmental pressures. It's no guarantee, but there could be certain universalities of life. The greatest hits of evolution on repeat across the universe. Each feature would be attuned to its local environment. Dimly lit planets would produce huge eyes to suck in extra light, like nocturnal mammals.
Some people have gone so far as to say that human-type organisms, humanoids, will occur on other planets.
The existence of other human-like organisms seems unlikely, given the long, convoluted chain of events that produced us. But we can't rule it out. If just one in every 100 trillion Earth-like planets produced a human-like form, there could still be thousands of creatures like us out there. Convergent evolution is also rampant in plant life, and C4 photosynthesis has arisen independently over 40 times. Would alien plants look like ours or something else entirely? On Earth, plants appear green because they absorb the other wavelengths in the sun's light spectrum. But stars come in many colors. And alien plants would evolve different pigments to adapt to their sun's unique spectrum. Plants feeding off hotter stars could appear redder by absorbing their energy-rich bluer light. Around dim red dwarf stars, vegetation could appear black, adapted to absorb all visible wavelengths of light. Earth itself may have once appeared purple due to a pigment called retinol that was an early precursor to chlorophyll. Some think that retinol's molecular simplicity could make it a more universal pigment. If so, we may find that purple is life's favorite color. Vegetation is more than just a curiosity. It's chemical information that could be seen from light years away. Earth plants leave a signature bump in the light reflected off our planet. Finding a similar signal from another world could point the way to alien vegetation. Perhaps this will be our first glimpse at alien life, a vibrant hue cast by a distant world.
What happens when you change the day length of a planet? What happens when you change the tilt of a planet? What happens when you change the shape of the orbit? What happens when you change the gravity of a planet?
Planets with long elliptical orbits would see drastic seasons. There could be worlds that appear dead for thousands of years, then suddenly spring to life. Most of the rocky planets discovered so far have been massive super-Earths. How would life evolve on these worlds? In the seas, gravity may not matter much at all.
A high-gravity planet isn't high gravity all over. If you're in the sea, and that's where all life starts, there's very nearly no gravity because you're much the same density as the stuff around you. It's when the animals come out on land that they feel the gravity.
High G-forces would necessitate large bones and muscle mass in complex life on land. They would also demand a more robust circulatory system. And plant life could be stunted by the energy cost of carrying nutrients under stronger gravity. Low-gravity planets would more easily lose their atmospheres to space and lack a magnetic field to protect from cosmic rays. But smaller worlds could be home to secret oases. Huge cave systems that provide hideouts for life. Possible habitable planets are estimated at 2.5% Earth's mass. If surface life does evolve on these worlds, it could be a sight to behold. Plant life could grow to towering heights, able to carry nutrients higher in lesser gravity. Without the need for bulky skeletons and muscle mass, animals could have body types that boggle the mind. Here on Earth, it took 3 billion years for evolution to produce complex plant and animal life. Simpler organisms are hardier, more adaptable, and more widespread. The largest collection in the Museum of Alien Life would likely be the Hall of Microbes. Yet finding even the tiniest alien microbe would be a profound discovery. bite-sized life could leave a big footprint. Like stromatolites on Earth, layers of microbes could build up into huge rock mounds over time, leaving behind eerie structures. And in big enough numbers, some alien bacteria could leave a distinct biosignature by exhaling gases that wouldn't coexist naturally, like oxygen and methane.
There's ways to make oxygen without life, there's ways to make methane without life, but to have them in the atmosphere together is almost impossible unless you've got biology making those gases at the surface. And it would have an imprint on the planet's spectrum of colors.
Next generation space telescopes could find a signal like this on a world not far from home.
The closest Sun-like star with an Earth-like exoplanet in the habitable zone is probably only 20 light years away and can be seen with the naked eye.
Most brown dwarfs are too hot to support life as we know it, but some are just cold enough. All the prime elements for life have been detected inside their atmospheres. And within these clouds, some layers would provide ideal temperatures and pressures for habitability. There could be photosynthetic plankton in these skies, kept aloft by churning upwinds. And with enough force, these upwinds could even support larger, more complex life. Predators. This raises a crucial question. What if we've been looking in all the wrong places? What if nature has other ideas? Most of the universe is too cold or too hot for liquid water and the biochemistry that supports life as we know it. But in case our biases are misleading, we have to cast a wide net to search for life outside the habitable zone, in places that seem wildly hostile to us. Exotic environments will demand exotic biochemistries, and while no element can match carbon's versatility, one contender is a frontrunner. At first glance, silicon seems similar to carbon. It forms the same four-way bonds and is also abundant in the universe. But a closer look reveals that these two elements are false twins. Silicon bonds are weaker and less prone to forming large, complex molecules. Despite this, they can withstand a wider range of temperatures, opening up intriguing possibilities.
Life based on the silicon atom instead of carbon would be more resistant to the extreme cold, providing a whole new range of weird forms.
But silicon has a problem. In the presence of oxygen, it binds into solid rock. To avoid turning to stone, silicon beings might be confined to oxygen-free environments, like Saturn's frigid moon, Titan. Its vast lakes of liquid methane and ethane could be an ideal medium for silicon-based life or other radical biochemistries. Without ample sunlight, beings on worlds like Titan would likely be chemosynthetic, deriving their energy by breaking down rocks. Such life forms could have ultra-slow metabolisms and life cycles measured in millions of years. High temperatures, typically rigid silicon-oxygen bonds become more flexible and reactive, triggering more dynamic chemistry. This has led to a truly bizarre proposal: silicon-based life forms that live inside molten silicate rock. In theory, these forms could even exist deep beneath the Earth inside magma chambers as part of a shadow biosphere. If so, then the aliens are right under our noses. Other shadow biospheres have been proposed, forms of life living alongside us that we don't even know are here, including tiny RNA-based life small enough to go undetected by existing instruments. Clouds of dust in empty space might seem like the last place you'd expect to find anything living. But when cosmic dust makes contact with plasma, a type of ionized gas, something strange happens. In simulated conditions, dust particles have been seen spontaneously self-organizing into helical structures that resemble DNA. These plasma crystals even begin to exhibit lifelike behavior, replicating, evolving into more stable forms, and passing on information. Plasma is the most common state of matter in the universe. If complex evolving plasma crystals really exist, and if they can be considered life, they could be its most common form. massive suns explode, some collapse into ultra-dense cores called neutron stars. Hulking masses of atomic nuclei crammed together like sardines. Conditions on the surface are mind-boggling. Gravity is 100 billion times stronger than Earth's. But beneath their iron nuclei crust lies something strange. A hot, dense sea of neutrons and subatomic particles. Stripped of their electron shells, these nuclei would obey entirely different laws of chemistry, based not on the electromagnetic force, but the strong nuclear force which binds nuclei together. In theory, these particles could link up to form larger macronuclei, which could then combine into even bigger supernuclei. If so, then this bewildering environment would mimic the basic conditions for life: heavy nucleon molecules floating in a complex particle ocean. Some scientists have proposed the unimaginable: exotic life forms drifting through the strange particle sea, living, evolving, and dying on incomprehensibly fast timescales. Life is not something that has to evolve naturally. It can be designed. And once intelligence is introduced into the evolutionary process, a Pandora's box is opened. Typical biological limitations, synthetic and machine-based life could be the most successful of all. It could thrive almost anywhere, including the vacuum of space, opening up vast frontiers unavailable to biological organisms. And compared to the glacial pace of natural selection, technological evolution allows exponentially faster growth, adaptability, and resilience. By some estimates, autonomous self-replicating machines could colonize an entire galaxy in as little as 1 million years. Can't predict how hyper-intelligent life would organize itself. But in theory, there could be convergent evolution at play. Humanity is at a tipping point. We stand at a crossroads of accelerating change unlike anything ever seen in the history of life. It feels as if the future could tip either way. Between utopia and apocalypse. The risks we face are daunting. But beneath the rampant pessimism for our future is evidence that humanity can not only survive the coming centuries, but thrive deep into the future. No one knows what comes next, but there are three broad paths our future could take. The first is collapse. A major catastrophe threatens the downfall of civilization and possibly even extinction of the human race. Second is plateau, where mankind averts collapse but hits an upper limit of progress. And third is transcendence, where humanity reaches its full potential, multiplies into the trillions, or transforms along the way into something entirely unimaginable. Envisioning these futures will clarify the risks we face and the promise we have as we step into an unpredictable new era for planet Earth and for ourselves. Mankind is no stranger to catastrophe. Our ancestors have survived asteroid impacts, ice ages, supervolcano eruptions, and deadly plagues, each time bouncing back to new heights. But our biggest threats no longer come from the natural world. They come from ourselves. Since the dawn of nuclear weapons, the threats of self-destruction have come to dwarf all others. By some estimates, the risk of causing our own extinction is over 300 times higher than extinction by natural causes. The Future of Life Institute identifies 4 main risks to our survival: nuclear war, climate change, biotechnology, and AI. To comprehend the gravity of these risks, we have to envision their worst possible outcomes. The soot from a large-scale nuclear war could cool global temperatures by nearly 10 degrees and wipe out up to 63% of the population. We have made strides in reducing nuclear stockpiles, but there are nearly 10,000 warheads still in existence. Currently, we are on track to heat the Earth by around 2.7 degrees by 2100, which could displace over 1 billion people. But in the worst case, we could trigger CO2 tipping points and cause up to 12 degrees of warming in the coming centuries. Biotechnology has the potential to solve major crises like food scarcity and disease, but could give small groups of people the power to cause global disaster. In theory, the release of a designer pathogen could have an even higher death toll than a global nuclear war. But the hardest risk to gauge stems from AI. It's the first threat we face that we may not be able to outsmart. It could become a powerful ally. Or it could ultimately outcompete us for the world's resources and push humanity into obscurity. Navigating this new risk landscape will be the biggest challenge we have yet faced. And new, unknown threats are bound to materialize the more we progress. But despite the potential for large-scale human tragedy, few of these risks on their own are likely to lead to our total extinction. In fact, we may be one of the least endangered species on Earth. Our sheer numbers and broad distribution have given us a geographical buffer against extinction. We inhabit every corner of the Earth, from desert to tundra and tiny isolated islands, which could act as natural quarantines in case of global disaster. Even if 99.9% of humans were eliminated in some catastrophe, 8 million of us would remain, more than existed for most of our history. And although we are slow to reproduce, we no longer rely on the glacial pace of natural selection to adapt. Technology gives us the power to adapt thousands of times faster than any other species in the history of life. Lastly, our generalist diets allow for a wide flexibility in food sources, a trait that was critical to survivors of past mass extinctions. Ultimately, the threat of collapse hinges on one question: how resilient is civilization? How big of a hit can we take and keep going? The Black Death of 1347 killed up to half the population of Europe and 1/10 of people globally. But even this did not derail human progress, and it was followed by the scientific revolution just 200 years later. The same proportional hit today would wreak havoc on our interconnected global economy. But as long as our infrastructure and knowledge remained, we could still rebound and maintain an upward momentum. If we suffered a collapse steep enough to extinguish global industry, it would make for a much longer, more precarious recovery. And if we somehow lost the capability for agriculture and were pushed back to hunter-gatherer lifestyles, the Earth could only support 10 million of us. Our population as it was 100 centuries ago. At minimum, there would need to be between 100 and 5,000 survivors to successfully repopulate the Earth. Below that level, the bottleneck would be too tight, and we might never recover. To comprehend what's at stake, we have to confront what extinction would actually mean. Our greatest threat comes not from a single disastrous event, but from the compounding effects of disasters that overlap and mix together in unpredictable ways. In 2009, 2 researchers conducted a thought experiment to see what it would take to drive humanity to complete extinction. Phase 1 sees a rapid crash in human population from global warfare and collapse of global industry and agriculture. Phase 2 sees the exhaustion of remaining natural resources over the following 2 centuries. And Phase 3 envisions a downward spiral of ecosystem collapse, punctuated by a supervolcano eruption, leaving the last remaining bands of humanity unable to cling on any longer. Such an outcome would not only be tragic for the loss of life, but for the loss of future potential life. Billions or even trillions of our potential descendants would never materialize. Distant planets would go unexplored. It would mark the end of music, poetry, and art in our corner of the galaxy, and possibly in the entire universe. The Svalbard Global Seed Bank in Norway now holds over 1 million seed specimens for over 4,000 species of plant, which could someday be a critical resource for rebuilding civilization. But there's an even better place to build a vault like this. Some have proposed lunar arks that would store genetic samples in lava tubes beneath the moon's surface. Here, they would be protected from global disaster, erosion, micrometeorites, and solar radiation. But the best way to secure our long-term survival is to take the leap that no other life form has ever taken. To become a multiplanetary species. Once a self-sustaining civilization is established on another planet, the chances of our extinction will plummet. We will carry our flaws with us, and we will face new and unknown risks the further we stray from Earth. But it will be worth it. A sustainable interplanetary civilization will be the foundation for a long and prosperous future. But is this higher future actually in reach? Or are we at the peak of our powers? How far can we go? In theory, it's possible that civilization will hold the status quo for the indefinite future, avoiding both collapse and transformation. there could be unforeseen barriers that keep us in a kind of uneasy stasis. But in reality, plateau will be a temporary state at best. In the short term, exponential changes in technology and Earth's climate will force civilization into new directions. And the further we push into the future, the greater the disruptions we will face. In the next few 100,000 years, we are due to face supervolcano eruptions and a new ice age, even if we burn every ounce of fossil fuels and bake the Earth. Without active climate management, the glaciers will have their revenge, as mile-thick sheets of ice steamroll huge swaths of North America and Europe. It's believed that around every 27 million years, Earth experiences a cyclical mass extinction caused by the Sun passing through the asteroid-dense middle region of our galaxy. And around 1 billion years from now, the brightening of the Sun will make Earth too hot for photosynthesis, and the oceans will slowly boil away, snuffing out all life on our planet. Modern civilization will not survive these events without a deep transformation. One option will be to let nature run its course on Earth and move to off-world habitats. Bishop rings are circular megastructures that could house over 1 billion people. They could provide over 3 million square kilometers of land, as much as India or Argentina. They could be built with lightweight carbon nanotubes, and their rotation would generate enough gravity to hold their own atmosphere. But if we decide to stay earthbound, we are not at the mercy of our planet. We have the power to write its future. Despite all the dangers we face, utopian futures are well within reach, and sooner than we might think. To our ancestors, our current powers would appear godlike. But everything we have achieved so far may pale in comparison to what comes next. Since the Industrial Revolution, technological progress has been radically improving the human condition in every critical way. Worldwide, quality of life is at an all-time high. We don't perceive these positive trends as clearly due to our negativity bias, which evolved to make us extra attentive to negative information. But the forward momentum is undeniable. Our course correction to a sustainable civilization now appears unstoppable. The costs of solar and wind energy are falling faster than expert predictions, making them often cheaper than fossil fuels. At the same time, converging advancements in AI and biotech are pointing toward a radical enhancement of human well-being. Already, projects like AlphaFold are discovering structures of pathogens and treatments for cancer far faster than humans could. There are over 10,000 diseases that are caused by single gene mutations, and gene editing tools like CRISPR have the potential to cure all of them. These upward trends are multiplying the human potential many times over. We are now the healthiest, wealthiest, freest, most educated, most advanced population of humans to ever exist. If these trends hold, we could gain the power to regenerate limbs, eliminate all disease, and possibly extend our lifespans indefinitely, putting us on the brink of the most radical transformation in our history. Achieving these breakthroughs will require technological leaps that the human mind alone cannot make. But already, NASA has begun to use AI to design mission hardware, outperforming human designs by a factor of 3. It's also being pioneered in the development of cleaner biofuels and drought-resistant crops, which could be critical in the fight against climate change. And this is just the start. We are witnessing the beginning of an intelligence explosion, which could lead to an artificial superintelligence that far exceeds human capabilities, able to solve complex problems that have defied humanity. Aligning it to human values will be a huge and novel challenge. But it will be a vital step, not just for the enormous prosperity it could bring, but to counter the threat of malicious AIs. A safely aligned superintelligence should be a prime objective for human progress. If we can safely harness the power of AI for human betterment, then we can paint a utopian future our ancestors could hardly fathom. A future free of disease and hunger, where biotechnology has stabilized the climate and biodiversity. Where abundant clean energy is developed in concert with AI. Where breakthroughs in rocketry and materials science have propelled humans to distant planets and moons. And where new tools for artistic and musical expression open new frontiers of beauty, experience, and understanding. And all of this could be just the prologue to an even grander future